Hello there everyone, I'm back. I finally managed to make part 2 of ultrasonic testing. The part should be coming through a lot quicker now after this one because I needed to look after some personal things in my life. However, let's just dive straight into it. The ultrasonic beam and wave types. And if you could hit like and subscribe, that would be highly appreciated. So let's go. The most important thing is to find out where does the ultrasound come from. Now in general applications of UT, we utilize piezoelectric crystals or crystals that have the piezoelectric effect to generate these ultrasonic vibrations into the specimens. We use different materials with obviously different pros and cons to select these crystals, and in UT the crystals are usually X-cut, meaning they're cut on the X-axis. So if I had a crystal, this is a very bad drawing, I'm sorry, I'm not an artist. So if we had a crystal that looked a little something like this, the X-cut would be through the middle of the crystal. This would be the Z-axis, and then this would be the Y-axis. Now we typically only use X-cut crystals, which give us something called a longitudinal wave. We'll get to that a little bit later. Just a quick word on some of the pros and cons. So lead zirconate titanate has good sensitivity and a broad frequency range, but it's brittle and limited under high temperature performance. Lithium niobate has high sensitivity and low acoustic impedance. We'll probably get to acoustic impedance in my next lecture on this. However, also limited in temperature ranges and very fragile. Barium titanate has good piezoelectric properties and can be used in high temperatures, though it has a poor frequency range and limited sensitivity. And then quartz, yes, this is regular quartz, similar to the crystal, although in a more refined state, but some people even have this in their gardens. They're very durable, as you can think, and the cons are that it's got a poor frequency range and limited sensitivity. Every NDT method is based on certain scientific principles, and ultrasonic testing can be said to be based on the piezoelectric effect. Now, the piezoelectric effect, the informal definition I have for it is the ability of some materials to generate mechanical vibrations when exposed to an electrical current, and to generate an electrical current when exposed to mechanical vibrations. So think about it this way. You have your UT set here with your screen, and this is connected to your ultrasonic probe. The probe is placed on a test piece or a piece of steel. Now, your set generates electricity to the crystal on the inside here. The crystal then generates sound that travels down into the material. The sound will hit the back of the material and be reflected back. This will then be caught by the crystal, who changes this mechanical vibration back into electrical. The electrical is sent back to the ultrasonic set, and on our screen we will see a response. The ultrasonic beam can basically be broken up into 3 different zones. The near zone, the far zone, and the dead zone. The dead zone is the first of the 3. And indications, this is very important, that indications lying in this zone will not be detected. So if you have your ultrasonic set, and before you plug anything in, you should see something on the left like this. So that's just a sign that the UT set is on. However, when you plug your probe in, you should see something like that. Now, this distance here is the dead zone. It's basically the ringing time of the crystal. And in this area, you will not be able to detect any indications because they will be totally masked by this echo. So now we get to the fun stuff. The second part of the beam is called the near zone or the Fresnel zone. And in this area, we will be able to detect discontinuities. However, we will likely over or underestimate their size due to constructive and destructive interference in this zone. The interesting thing is that the size of the near zone can actually be calculated, and we have a formula for it. It's pretty simple. The size of the near zone is the square of the diameter of the transducer over the wavelength. Now, the wavelength, if we remember, so this is only for the wavelength here, is equal to v over f, velocity over frequency. So we can also write this formula as diameter squared over 4 multiplied by velocity over frequency. So we can cancel this frequency out and move it to the top here. Now, this leaves us with the formula d squared multiplied by frequency over 4 multiplied by velocity. And this should give us our near zone. I recommend using this one since it spares you one calculation. It is a little bit more difficult to memorize, I guess, but in the long run, I think this is the way to go. Okay, so let's get down to business. This is typically the type of question you will be asked. So let's calculate the near zone for the following. We get a transducer diameter, a wavelength, a frequency, and a speed of sound. So we'll use my formula. Before we even get to that, please remember to put the comma in there. We want the answer to be in millimeters, and this should ensure that the answer is in millimeters. So my formula says d squared multiplied by f over 4 multiplied by v. So that's the square of 25 multiplied by 2 in this case, divided by 4 multiplied by the speed with the comma in. So this is 625 multiplied by 2 divided by 4 multiplied by 592. And if we punch this into our calculator, it should give us 52,787 millimeters. Now, you'll have to ask specifically to what degree do you round. I typically leave all my answers to the third decimal. However, this may change depending on what school you're attending or what the actual lecturer wants. Let's do another one. So in this one, you'll only be given the information that this is a shear wave probe. So in this case, this actually gives us a clue as to what speed we're going to use. So in most mild steel, the speed is between 3,200 meters per second and 3,300 meters per second. That's the range. Typically, I always used 3250, but please make sure from your lecturer what speed they would like you to use. Now, once again back to our formula. Near zone is equal to diameter squared times f over 4 times v. Once again, the diameter is 25, so the square of 25 multiplied by the frequency is 2 times 4, and then we're going to use this, but I'm going to put the comma in there. So 3,25. And if you punch this into your calculator, it should come out to 96,154 millimeters. Now, the final part of the beam is called the far zone, or the Fraunhofer zone. And in this zone, we can accurately detect and assess indications. In this zone, the beam will gradually spread out, losing its energy the further it goes. The formula to calculate the half angle of the beam is sine theta is equal to a constant. Now, the constant is here. These are some typical constant values. However, you may want to ask the course that you're in just for the values that they use. It may differ from these. So it's constant multiplied by wavelength divided by diameter. So let's do it this way. Sine theta is equal to constant multiplied by V over F over D, which, to make it simpler, sine theta is equal to constant multiplied by velocity over diameter multiplied by frequency. Once again, this makes it a little bit shorter and a bit easier to do. Hoekom verander jy? Now these questions are typically a little bit more difficult, but let's work through some examples. So we're given the question, you're using an ultrasonic transducer with a diameter of 20 millimeters. The ultrasonic wave you're using has a frequency of 3 megahertz. The speed of sound is 5,920 meters per second. And we're asked to calculate the setup to the 50% isobar. So first things first, we're going to put in the comma there. And the 50% isobar, we can check our K values in the previous slide, but it should be 0.56. Now we're going to write down the formula. So sine theta is equal to the constant multiplied the velocity divided by the diameter multiplied by the frequency. Now the constant here is 0.56. The velocity, remember to put in that comma, and then the diameter here is 20 and the frequency is 3. Now at the end of the day, you should come to something like 0.05525, etc., etc. Now it's key to remember that this is not the answer. We still need to solve this half of the equation. Now in order to get the angle, we need to move the sign to that side. So we're going to say arc sine, and then we're going to put this value in here. So 0.05525, etc. Or now just also on your calculator, this may say sine minus 1, arc sine, same thing. And then we should get something like 3,167 degrees. Now, the next tricky part to remember is this is the half angle. The formula gives us the half angle. So in order to get the full angle, really easy, we just multiply it by 2. So if we multiply that by 2, we get 6,334 degrees. And this should be your full angle of beam spread. Right, let's try one more. In a different scenario, you have a transducer with dimensions of 10 millimeters. You're using an ultrasonic wave with a frequency of 5 megahertz and a speed of 3,250 meters per second. Calculate the beam spread for the 20 dB isobar. So first step, we put in the comma. Second step, we look at this isobar And this K value, this is also our 10% K value. It's also known as the 20 dB. And it is equal to 1,08. Next step, we write down the formula. Sine theta is equal to constant multiplied velocity over diameter multiplied by frequency. So let's plug in the values. So 1.08 multiplied by 3,25 divided by 5 times 10. If we do this correctly, we should get 0,0702. Remember, this is still sine theta that's equal to that. So to get our angle alone, we do arc sine with this value, and that should give us 4,025 degrees as the half angle, which would then translate into 8,05 degrees as the full angle of beam spread. Alrighty. So now that we've run through the calculations for this, let's do some theory as well. Now in ultrasonic testing, you get 4 main types of waves. The first one is the compressional wave, which is also called a longitudinal wave. And these are generated with X-cut crystals. Something to remember on this, so each of these will typically have a keyword. So if you note the word longitudinal, the particle vibration is parallel. So whenever you see a question with the word parallel, that's all those L's, they mean longitudinal. It has alternate compression and rarefaction zones, and this is the wave with the biggest speed. So what's meant by a compression and a rarefaction zone? If this is the particle at rest, once the energy is impacted on it, it will compress, so it will become like more egg-shaped. This is the compression zone, and then it will release this energy, so it will become more like this. And this is the rarefaction zone. Now on a graph, this will typically be a good old sine graph to show what the compression zones are and what the rarefaction zones are. The next wave type is called the transverse wave, but it's also called a shear wave. And in this case, the propagation is perpendicular to the direction of movement, meaning your particles will vibrate like this, but your wave will move like this. So your particles are almost like rubbing against each other, causing the wave to travel further into the material. The speed is roughly 50% that of a compression wave. This differs from different materials and basically different elasticities, but it's roughly 50%. And a good thing to remember is that these are generated by using diffraction, and we only use X-cut crystals in ultrasonic testing, or at least almost only use it. We don't use Y-cut crystals in conventional ultrasonic testing. The next wave we're going to talk about is a surface wave. It's called a surface wave because it travels on the surface of a relatively thick material. It doesn't penetrate deeper than one wavelength, and the particle motion is elliptical, almost like a corkscrew running through or on the material like this. Now, it's slightly slower than a shear wave, about 90% of the shear wave speed. And the cool thing about these waves is they can actually travel around bends. Maybe not sharp corners, so like that, no. But like this, yes. And they have a depth of less than one wavelength. So then we get the Lamb wave, and the Lamb wave has two modes of propagation. It's symmetrical and asymmetrical. So symmetrical will look a little something like this. Whereas asymmetrical will look like this. Now, Lamb's waves are dispersive, meaning that they have different frequencies and different travel at different speeds in the material. And typically they will travel through the entire thickness of a thin material. Now remember, Rayleigh waves, thick material, but they only travel to less than one wavelength, where Lamb waves are typically in thin materials, less than one wavelength, 3 wavelengths thick, but they travel through the entire piece of material. Alrighty, so let's recap. We use crystals to generate sound. We use X-cut crystals that generate longitudinal waves. The piezoelectric effect is the ability of certain material to convert mechanical energy into electrical energy, and vice versa. The dead zone is that extension of the initial pulse, and no indications can be detected there. The near zone, the formula for that is diameter squared divided by 4 wavelengths, or d squared multiplied by frequency divided by 4 times your velocity. And due to constructive and destructive interference, we will be able to find discontinuities, but not accurately size them or evaluate them. The far zone, we have the half angle formula, which is sine theta is equal to constant mole times the wavelength divided by diameter, or the constant times the velocity divided by the diameter times the frequency. Remember to use the arc sign, or sine to the power -1 in this, and remember that we're calculating the half angle, not the full angle, and the far zone is where we can find and accurately evaluate indications. So, compression waves, their direction of propagation is parallel to particle movement, and they have alternate compression and rarefaction zones. The transverse or shear waves, the direction of propagation is perpendicular to particle movement, and the speed is roughly 50% that of a compression wave, and it's made by utilizing diffraction. The Rayleigh wave has an elliptical propagation movement. Its speed is roughly 90% that of a shear wave, and it can travel around corners, or bends rather. And then Lamb waves are symmetrical and asymmetrical and travel through a thin material. I really hope you've enjoyed this presentation, and if you are really struggling with some ultrasonic concepts, please feel free to drop a comment down, and the next lesson's coming up. Hopefully I'll be able to cover some Snell's law and some of the more interesting aspects of ultrasonic testing. Until next time, goodbye.